I think whatever we had in, oh yes, I forgot something. In spectrophotometry, if you have several chemicals that absorb a specific wavelength, keep in mind that absorbance can be due to several things. And you had a homework about it. Molar absorptivity for the first chemical times the path length times concentration of the first thing, plus molar absorptivity for the second times the path length times the concentration for the second thing, and the third, and who knows how many we have, but you have to add them up, right? So hopefully you practice doing that homework. So that can be on the test. Just Beer's law. I guess that's kind of it. Okay. Let's look at this question. How does a liquid-based ion-selective electrode work? Right. Woo. Use the picture below and explain the principle of the liquid-based ion-selective electrode. So, you're supposed to have an electrode that is very, very selective for a specific ion. Let's say the ion is C+. Okay. So we will determine the concentration of C+ in the solution up here in the beaker. How we would do it? We would need two silver-silver chloride electrodes. One will be inside of the filling solution and one will be outside. And the membrane of that ion-selective electrode is the most important part. So let's look at the membrane. The membrane will have our cation, which the membrane is very hydrophobic. What are three requirements for the membrane? We did it today during the lecture. So, anybody? Three requirements. Conductive, selective, non-soluble in water. Okay? So, how is it non-soluble? Our membrane is a polymer, very hydrophobic, not water soluble. Okay? How is it conductive? It has ions that can, move in and out. That's making it conductive. Let's see what else. This polymer is filled with a liquid, which is hydrophobic. It will not mix with water. It hates it. But guys, in order for this electrode to work, we need to have some kind of ligand. And you do not have to memorize ligands because they're so different for different ion-selective electrodes. What you need to know that our analyte should complex with a ligand and have a huge formation constant. Okay? So this is the preferable form of analyte whenever ligand is around. But even this high formation constant still means we would have a tiny amount of free ligand and analyte in the hydrophobic environment. The hydrophobic environment is really harsh for C+. C+ loves water. It hates the hydrophobic environment. So if we have a tiny amount of C+ in the membrane, free C+, it would love to move out to water. Okay? But don't forget, if C+ moves, we have something hydrophobic, that is R-, that will be like, please stay behind. I want, to have a neutral charge. So R- is an anion that is also hydrophobic. it will not be mixing with water. Okay? So far, makes sense? You can say anion, hydrophobic anion. You can say a ligand that forms a very stable complex with a analyte. We have our analyte C and some other water-soluble anions in water. And we have an analyte C and some water-soluble anions in the filling solution, up here. They can be exactly the same or different. I'm talking about anions. Usually different. All right, so whenever C+, free C+, leaves the membrane, it leaves R- behind. And it will not be, why does it happen? Because C+ hates hydrophobic. It wants to be out. If C+ moves out, R- is behind. And we will have a junction potential developed. And in some cases, C+ will go back whenever equilibrium is established. Okay? So the same number of C+ will go out as C+ will go in at some point, whenever the equilibrium is established. And we will have it inside of the membrane and outside of the membrane. So we will form a junction potential inside and junction potential outside. So far, makes sense? Whenever they make that membrane, it's just filled with C+, guys, by design. It has a lot of C+ and L and R-. R- loves that environment, L loves that environment, C+ hates it. But whenever it's complex, in a complex form, it's okay. But as soon as, if they divorce, C wants out, to be out. That's in Low's environment. Sounds good? All right, so potential for the cell that will be measured between one reference and another will be due to junction potential outside minus junction potential inside. And it will be some kind of constant, minus 0.0592. If we are talking about C+, it means it will be divided by 1, so it's positive 1, times log of activity of C+. So let's see, what are all of these? Okay, what are required potential of these species, properties, okay. Okay, ion selective electrode, how is it measured? This silver chloride measures junction potential outside. This silver chloride measures junction potential inside. Junction potential inside will be a constant because the filling solution is not changing during the experiments. But outside solution, analyte solution, changes. Okay? So that's why outside the junction potential is changing. Okay, we can make a calibration curve of potential versus log of activity of C+, and you can see that the slope will be positive, 0.0592 divided by 1, and the intercept with the y-axis will be a constant. So if we have a few standard solutions of C+, we can make a calibration curve, right? And this is that constant. And potential versus log of activity. is linear. Not potential versus concentration or activity, but logarithm of activity. That is linear. Good? All right, let's see if I answered that. Properties of these species, how? Okay, ion selective electrode is measured as a difference of junction potentials outside and inside. It's a, what type? I really wanted you to tell me it's a junction potential. Okay, if our ion selective electrode is for potassium, then we would have activity of potassium here, but it would be exactly the same thing, okay? Potassium is +1, that's why we have +1 here. Okay. If you get a solution with unknown potassium activities, you measure potential and find log of activity, and finally activity of potassium. Good? Imagine if it's an ion selective electrode for calcium, what the difference will be. It would be +2, right? And the slope will be twice smaller, right? Make sense? The rest would be very similar. Questions?
What are A minus and B minus again?
A minus is just the anion, water soluble or hydrophilic that the analyte has. You cannot just have potassium ion by itself. It's the anion in the analyte solution, aqueous, or hydrophilic. That's what I wanted to say. And B minus is the same thing in the filling solution.
Thank you.
Good? Question? I really recommend you to finish the homework.